We will be recording this meeting. You should see a pop-up on your screens right about now saying that this meeting is being recorded, and we will make these recordings available to you all after the event as well, in case you're not able to attend the full thing, or you would like to, other people who can't be here right now who would like to see what we're talking about. All right, so Ariwan, do you want to share your screen?
Sure, yeah. I can't do it just yet though. It says host disabled.
I need to allow people to share their screen. There we go. That should be working now. All right. So our first talk is by Ariwan Adisuhairi at Cambridge, and it's entitled "What Must the Learner Learn? The View from Vowel Harmony." Take it away.
All right. Hi, I'm a third-year student at the University of Cambridge, going to graduate soon, and today I'll be talking about some topics in the learning of vowel harmony systems. So my focus will mainly be on the treatment of neutral vowels. Although I did want to talk a bit about transparency and predictability and underspecification. So we generally assume that vowel harmony is phonological in nature, right? But it's kind of unclear how transparent the alternation has to be in order for it to be recognized as phonological rather than some kind of allomorphy. One usual diagnostic is naturalness of role, but because we are working in a substance-free theory, any segmental mapping is in principle computable by the phonology. So that isn't really a proper diagnostic. There's also the diagnostic of whether it affects one segment or multiple. And in the usual cases of vowel harmony, we do have like one-to-one mappings, maybe differing only on one feature. But there are some languages where, say, vowel harmony produces like diphthongs. So in this Kesab dialect of Armenian, thanks to BirdVox for the data, the front allomorph of the plural suffix, this big O, is actually a diphthong with a central component. It's not clear whether the diphthongs are actually bimoraic and hence occupy two timing slots, but I think if it does, it kind of raises a bit of a problem, right? It is possible to say that this is just a front rounded vowel with surface vision, but there are front rounded vowels elsewhere in the language, so there must be some ordering of roles here. Yeah, and there's also the example of the Hungarian present tense alternation, where you get like a very different allomorph. And Tobias Scher analyzes it as some kind of floating segment thing. Yeah. So in general, there's a question of how do we demarcate between maybe crazy phonological rules and morphology. Maybe we can have a hypothesis saying, okay, there's no melodically conditioned allomorphy and start from there. Yeah. All right, moving on to neutral segments. So we usually have transparent and opaque segments, which are somehow defective triggers for vowel harmony. And I'll be talking about three ways of treating the issue. So one way of doing it is by treating them as completely unexceptional. So there's nothing really different about neutral vowels in their featural composition. And in a lot of cases, we really have to say more about the rule component. So somehow the rules have to skip neutral vowels. So in a search and copy theory, we set the rules up such that they search for all the vowels except the neutral vowels in transparency, right? But in some languages like Finnish, you can't really do that on its own. So Finnish has this surface inventory, neutral vowels I and E. How do we characterize the set of harmonic vowels as targets of search without also including I and E, right? On the assumption that all of these segments are fully specified, there's no differences. Well, we can't really do that because this is not a natural class of segments. So one possibility is to do with rule ordering. And some people have proposed this for Votic. In Finnish, it doesn't work because Finnish has a lot of disharmonic loan stems. So you have transparent I following a front vowel and transparent I following a back vowel. And either ordering of the rule for vowel harmony will generate the wrong results in some of the stems. So in my dissertation, I argued that rules had to be expanded so you can allow featurally unnatural rules in some ways. It's not a very nice result. One way of doing this is by allowing a conjunction of natural classes via set union in some way. Or it's another alternative was to allow rows to apply simultaneously but be distance sensitive, which kind of abandons a key tenet of relativized locality. Basically, the idea was that a search would start out from the edge, from the suffix, and target either a low vowel or a round one. And the idea was that you kind of bypass the locality restrictions and ordering paradoxes that arise from row ordering analysis. But the cost is that you have to interpret locality in a very different way, which is not that, it wasn't very, very well received. And there's not that much other evidence for the approach. So it's not that great. And the other, so another common way is by underspecification, right? So you leave the neutral vowels underspecified for the harmonic feature somehow. Maybe it's because they're not contrastive, but there are languages where the neutral vowels are contrastive, at least on the surface, with some other vowel and still don't participate in vowel harmony. And maybe something to do with ambiguity, like the fact that they can be followed by both back and front vowels leads the child to treat them as maybe underspecified. I think Harry Vanderhaus has proposed something along those lines. But suppose that a transparent segment is, a neutral segment is underspecified for the feature. We want to say, so that it's skipped, right? Let's say a search for back will skip I if it's 0 back. It'll just pass through. But we also need to explain why these transparent vowels just don't just alternate, because they should also fall under the structural description of the search rule, and that they should also initiate searches for back values. So usually people say, okay, there's structural preservation, blocking them from becoming back, or you have surface neutralization. And again, this only works if you have the neutral vowel which lacks a surface counterpart. And we can also get opacity through underspecification, which I won't really cover. Right. And the main thing I wanted to talk about today was this idea where you can have vowels differing in their back values depending on the context. So again, Harry Vanderhaus has worked on this. For example, in Finnish, you have I, which is plus back after plus back stems, or else it's minus back. And you have a bunch of other alternatives. So in this case, the child must actually learn the link between the backness of a neutral vowel and its stem context. So you can have some kind of morpheme structure constraint that applies when a stem is lexicalized. So if, for example, in analysi, where I follows a back, a non-back vowel, it will be treated as actually I. Otherwise, if it's followed by a back vowel, then it will be treated as back. Right. And again, we need the contrast to be neutralized on the surface. Presumably, we delete the back value and insert minus back by default. And this is just a very traditional absolute neutralization analysis. So it's subject to Kapowski's original arguments against it. Although he actually criticizes something along these lines in his paper on abstractness, but the main argument wasn't that relevant. Like he said that okay, this analysis is very artificial and that it fails to link the MSC with the absolute neutralization of the two vowels on the surface. Hopefully I'm not misrepresenting it too much, but it doesn't seem overly relevant. Although, again, the traditional arguments against absolute neutralization, like the non-attestation of splits, are still relevant because this analysis makes heavy use of neutralization. And of course, in this 2D example where you have context-free backness, it's just a context-free sound shift. And we also want to know how much evidence the child needs to learn these abstract segments, because I mean, on the basis, like from what I know, generally these abstract segments are proposed to account for something in vowel harmony, right? But other rules like palatalization don't seem to be sensitive to whether or not this I is underlyingly or not. Which is not necessarily a problem, right? Because vowel harmony is fairly widespread throughout the system. So maybe it's not an issue, but we would like to know what the evidence is how much evidence is required to posit an abstract segment. Yeah. And there's this issue of assimilation in Finnish also, where the front vowels condition assimilation. But it's not really a problem in substance-free phonology again, because you can just say plus high minus round condition stabilization. It's
That's
unnatural,
9
but it
minutes.
doesn't matter. All right, I'm almost done. Yeah, okay. And there are languages where, as mentioned, neutral vowels aren't unpaired, so like Votic and Seto, which do have contrast between I and its back counterpart. Either way, because we want to have a contrast, the analysis above would have the contrast be neutralized on the surface, right? But again, it doesn't apply in the low-end forms in Votic, where you do have you could appeal to like lexical strata or something like that. It's always a possibility. And again, you have languages where neutral vowels are only neutral in some contexts. So for some rules, they are neutral. For others, they are harmonic. Again, how we can't really treat this in terms of absolute neutralization, especially if the rules apply in the same phonological stratum, which they do in Kyrgyz, but not sure about Kachavan Armenian. Yeah.
All right, that's 10 minutes, so maybe start summing up.
Yeah, so hopefully I've shown that neutrality continues to be problematic for phonological theory, including substance-free phonology. There are a few ways in which we can analyze neutrality, but none seems to be an all-encompassing account. And more generally, we also want to decide between, have a good way of deciding between allomorphy and morphophonology. And unfortunately, I didn't get to discuss what happens when features are emergent. So like if you have very completely arbitrary features, like in Dave Oden's work. Yeah.
All right, thank you, everyone. So we'll now have about 5 minutes for Q&A. So if you have a question, you can raise your hand, which I see that several people have done. Let me see if I can get a list of who has done that. That all happened so quickly, so I have no concept of who raised their hand first there. But Bert, you have a question? Oh, I see. That's just people applauding. All right. My bad. Yeah. If you could put raise your hand if you have a question, or write something in the chat to indicate that you have a question. Pavel.
Yeah, thanks. Thanks, everyone. Thanks, Sami. So, I mean, obviously, my question is, I think, if you could just say a little bit about how you define the contrastivity, right? Because, whenever you say things like, oh, this vowel is, like the problem with Votic is always that, is that it's neutral, but it's not like it's missing the, the contrastive counterpart. And I think, I see a lot nodding vigorously, which which is always the question, how do you know, what is your sense of contrast beyond having like a very minimal counterpart? And if that influences your conclusions in any way.
Right. Yeah, I know you can define it in terms of hierarchical contrast like Daniel Hall does, where he actually gets Votic to have I to be like split off before every other vowel and treated as neutral. And I suppose that works, but in my dissertation, I argued that it doesn't really work with a Hungarian. Like there's no way of splitting the feature tree in that language such that you just get I, E, and to be neutral. But Hungarian is very messy, so I didn't talk about it here. Like I actually tried to like draw a bunch of trees or plan them out such that you can try and show that it doesn't really work there, because it doesn't work. Like contrastive hierarchy doesn't allow you to explain it via underspecification. There could be other explanations out there. Yeah. And of course there's pairwise contrast, yeah, which I have no real opinions on. Yeah.
Do we have any other questions for Ariwa? If not, then I think we're about the time where we should move on to the next talk. So thank you, Ariwan. And if you have further questions, I'm sure that people in general, this goes for all speakers, be happy to keep discussing later on, for example, by email if you have additional things that you think of. So our next speaker is Islam Yusuf at the University of Southern Norway, and his talk is entitled "The Problem of Arabic Marginal Emphatics: What Learners Really Need to Learn." Go ahead. Islam, are you there? I think we can't hear you right now.
Okay, I need to unmute myself. Can you hear me now?
There we go. Perfect.
Okay. Yeah, thanks. So good evening, afternoon, morning, everyone. In this talk, I'm going to discuss how to use substance-free feature theory to resolve the problem of Arabic marginal emphatics. First, the goals of my talk are as follows: to introduce the phenomenon of emphasis and varieties of Arabic, to present the controversial issue of marginal emphatic consonants, to argue, based on evidence from contrast and phonological activity, that learners acquire an emphatic vowel phoneme instead, to establish that what learners really learn is substance-free phonological features which define natural classes, not segments, to present a minimalist model for formulating substance-free representations of segment inventories, and finally to provide a uniform representation of the Arabic underlying emphatic segments and demonstrate how learners learn emphasis in that model. So without further ado, what is emphasis? Emphasis being described by a number of labels, the most widely accepted of which is pharyngalization, and it can be defined as a type of secondary articulation involving tongue root retraction. In acoustic terms, emphatic sounds are marked by F2 lowering, or more precisely narrowing of the F1, F2 difference as compared to non-emphatic sounds. Emphasis is almost never an articulatory feature of only one segment. In other words, it always spreads in what is known as emphasis spread, which we can define as assimilation of the emphatic feature to adjacent segments throughout a particular domain. In this domain, the quality of both consonants and vowels is affected to varying degrees. So to give just one example from the Cairene variety, we get batalna, where you hear backing of all consonants in the uninflected word domain. So emphasis spread also exhibits variation in the dialects with regard to identity of the contrastive emphatic triggers, which will be our concern here, but also in terms of domain of application, directionality, and opaque segments. Now, the great majority of Arabic dialects contain a set of pharyngalized coronal consonants known as emphatics or primary emphatics. And depending on the dialect, these comprise a subset of pa, sa, za, ba, va, and sometimes ra and la, depending on the variety. So for example, we find these slightly different sets in 3 varieties of Arabic, as you see on the slide. These segments play a major role in the phonologies and inventories of the dialects in various respects. One is that they distinguish numerous minimal pairs where they contrast with the plain counterparts. So you get toba, toba, nasib, nasib, for instance. They occur in almost any environment, in particular next to low, mid, and high vowels alike, in addition to all consonants. 3, they persist throughout all derivations of a given root. And 4, in items that contain one of these primary emphatics, all other consonants may surface as emphatic as well, which we call conjunct secondary emphatics, which appear in all positions. So the conclusion is that pharyngalization is contrastive for this class of consonants, they are underlying emphatics. Now, in addition to the primary emphatics, most researchers add a class of marginal triggers where emphasis spread, mainly lowering of a to ah, is documented in stems with no coronal emphatics. These are composed of labial, dorsal, and coronal consonants. The list includes all or several of these consonants depending on the dialect. Again, ma, fa, ba, ha, ha, ka, na, and ra and la as well. The main question regarding these marginal emphatics is, do we include them in the inventory or not? Given that 1, they're statistically rare, 2, they're restricted in distribution, so we found them only in syllables containing a low back vowel, and 3, sometimes they're claimed to have a smaller domain in terms of spread. Instead, what I believe learners actually learn is an underlying emphatic vowel, which they learn based on 2 striking observations. One is that all consonants are pharyngalized in syllables containing a low back ah, and two, that only the primary emphatics occur next to non-low vowels. So if there is no primary emphatic in the word, only surface emphatic consonants are found next to a back low vowel. Therefore, learners have evidence that ah is a contrastive segment, is a contrastive trigger of emphasis spread, which supports the claim that there is a phonemic split in the low vowels in most varieties of Arabic, I believe. Now, how else do we know that learners learn ah? Well, learners are inclined to make fewer distinctions in the contrastive inventory, that is to learn the most minimal system possible. So there is one ah phoneme instead of many marginal emphatic consonants. Two, they learn this also because they encounter a lot of minimal pairs involving ah and ah contrasts parallel to the primary emphatics. You get ab, ab, bosh, bash, and so on. This solution is also reinforced by the fact that a foreign loanword with a back low vowel is interpreted as emphatic in Arabic, as we see in the word lamba. And often with a primary emphatic, if the word contains a plain cornel in the source language, as in pantalon for pants or busta for post. Here, the change to a consonantal trigger must have been originated by a vocalic trigger, since the source language, Italian or English, obviously has no emphatic consonants, right? So what do learners really learn? I believe they learn a substance-free phonological feature corresponding to emphasis. These substance-free features are the building blocks of contrastive phoneme inventories. And these features also need to be privative, autonomous, minimally specified in language particular. Most importantly, features exist only as needed for a given inventory, in line with representational economy and the Toronto School of Contrast. Features are also discovered or learnable on the basis of actual linguistic experience, where they are perceived as abstract categories learned on the basis of generalizations that emerge from phonological patterns in line with emergent feature theory. Features often behave together as units as well. Units organized under higher order categories known as class nodes. This is, of course, the premise for most models of feature geometry. And further, I believe that features are organized as in unified features theory, namely that consonants and vowels utilize the same features, which are linked to distinct but hierarchically related nodes. So which hierarchical system is learnable? The framework I proposed for the analysis is called the Parallel Structures Model Feature Geometry, which was first introduced by Bruce Moraine in 2003. It is a minimalist, substance-free, restrictive model incorporating insights from various other models. Parsimony as a way to achieve structural economy is the core principle of the PSM, from which all the architecture and the machinery follow. It is accomplished through the following basics. One, segments are represented using a minimal machinery of structures and features. So minimal in the sense that no more features or structures should be used than are necessary. Two, consonants and vowels utilize parallel structures and features for place, matter, and laryngeal features whenever possible, as we see in this diagram. In this way, the model promises to capture all consonant-vowel interactions in a unified manner. Three, feature combinations are maximized. Four, every complex structure entails a less complex one. So for every segment with complex structure, there exists one or more minimally different segments with a subset of this structure in the inventory. And finally, major class features like consonantal and sonorant are classified structurally through the presence or absence of matter features. So how do learners learn the emphatics then? On the one hand, the presence of non-primary articulation is what typifies emphatic consonants. So emphasis should then be represented as a dependent node in the PSM. Let's just call it dependent. This motivates the choice of the emphatic feature, which could be either DEP, dependent, class 1, F. If you believe in radical substance-free phonology, that phonology has no access whatsoever to the phonetic content of distinctive features, or something like the place dorsal, if you want to go for the convention of stating your features in phonetic terms. This feature then characterizes. Thank you. This feature then characterizes the natural class of underlying primary emphatics plus the ah vowel trigger. Now, Since this is a vocalic or dependent feature, the simplest segment that is composed of that feature, nothing else, is A, whereas the front A is composed of a V matter open feature and no place features at all. From also primary emphatics have this feature in addition to a primary C place coronal feature plus various other matter in laryngeal features. From these segments and the emphatic feature will spread bidirectionally, as we see in this diagram, within a specified domain, whereas in the diagram we see the X representing any consonantal or vocalic trigger. What does a full system in the PSM look like? Well, without going into details here, this is what the inventory of Cairene Arabic looks like in the PSM, where only 11 features cross-classify 33 segments. You find natural classes grouped by feature or class node, for example, labials, coronals, secondary coronals, which include both consonants and vowels, stops, fricatives, and so on. You can ask me about that later if you like. So to conclude, first, in addition to the primary coronal emphatics, there is an emphatic vowel A. This means that the classical marginal emphatics are underlyingly plain consonants, which become targets of emphasis spread that is triggered by that segment. 3 underlying emphatic segments, whether they are consonants or vowels, form one natural class that is distinguished by the feature def class 1F or V place dorsal. I prefer the latter. I like to call my nodes place and matter and refer to my features as labial, coronal, dorsal, open, closed, and so on. Why? Because I believe that there is, after all, overwhelming similarity between phonological and phonetic categories due to the universal articulatory and acoustic properties of speech sounds, despite the autonomy of the two systems, of course. Substance-free features then behave independently as odd segments, as we've seen for the emphasis spread patterns. I hope to have also shown that the parallel structures model provides an economical and substance-free way, or possibly substance-free way, of capturing the internal structure of phonemes in natural language, and that the model provides a unified analysis for consonant vowel interactions. My point here is that we can't group consonants and vowels together with full specification or in substance bound theories. That was all. These are my references. Thank you very much for your attention.
All right, thank you very much. We have a question in the chat from Jonathan Roski. Can you go over exactly how a learner learns these features from data? So what exactly is the learning process there?
Right. So I don't follow the contrastivist hypothesis model here, where the feature, we start with the features sort of and get to the segments, but you will have to have evidence from the phonological activity from the process itself, in addition to contrast with other segments. So you find a minimally different phoneme, for instance. So there is feature X that would be different between these phonemes. And then evidence for that feature could be found in a X or Y phonological process, right? So if you prefer your features in sort of a phonetically labeled, so a dorsal feature or a back feature would correspond to emphasis, or some other feature would correspond to coronality, and then build up those features based on phonological activity bit by bit in the minimalist possible way. And then you have this whole system altogether to look at, and you know, use the fewest possible number of features. I hope that answers the question to some extent.
Right. We have time for at least one more question from Josep Dolatian in the chat. I wonder if additional evidence can come from Arabic pedagogy. I have vague memories of seeing Arabic for English speaker textbooks, teaching students to focus on the articulation of the low vowel in order to learn emphasis.
Yeah. Well, it's been mentioned in a couple of references. I kind of talk about that briefly. You know, if you take just any English word with a back vowel, say you know, sun, it doesn't have to be ah, and then you just take that into any Arabic dialect, and you get suddenly you get an emphatic, right? You get a sa. So learners would quite intuitively do that, and so you could say that there is always, you know, a vowel-like trigger At least it starts that way, and then maybe that word, if it becomes an established loan word, it will acquire a consonantal trigger, if you will.
All right, we have 2 more questions, which unfortunately we will not have time for. I'll try to keep us running roughly on schedule here. So Fabian and Charles, if you want to ask your questions to Islam in private or by email, feel free to do so. That brings us to our third talk by Shanti Olsbjørnen, who's at the University of Deusto. And the talk is entitled Feature Spreading and Substance-Free Phonology, the View from Element Theory. And Shanti, do you want to go ahead and unmute yourself as well?
Okay, sorry, can you hear me now?
Perfect.
Okay, and can you see the screen? Sorry, can you see the?
Yeah, absolutely.
Yeah, okay, great. Right, so this talk is indeed on feature spreading and substance-free phonology. It's a view from element theory. Basically, the aim of the talk is to say that a substance-free element theory with its freedom of phonetic interpretation is what can allow us to make intuitive, computationally simple, spreading-based analyses even more possible than what autosegmental phonology had originally imagined. And this is desirable because many empirical patterns are best expressed by feature spreading. And in fact, we just saw a nice example of it there with the emphatic spreading. This is, in fact, the ability to handle feature spreading operations is what promoted autosegmental phonology over just linear SPE, where spreading is often awkwardly captured. And it is widely accepted in phonology that this is the approach that we should take. But I think it's only been maximally explored by government phonology due to element theory. So in terms of spreading, Graph uses mathematical techniques to compare SPE with government phonology. And he says that the unexpected result is that government phonology corresponds to a very weak fragment of SPE, yet it can attain the full expressivity of SPE through more powerful mechanisms of feature spreading. Why is feature spreading so rampant or so easy to do in government phonology? Because we use element theory. Element theory, which has original basis, Donegan of natural phonology has an early paper on it. Dependency phonology, the framework, and particle phonology all use element theory. And what it is basically is a set of features which are privative, they have autonomous interpretation, and they are uniform between consonant and vowel, something that we saw that was very useful in the previous talk. Harris and Lindsay point out that the autonomous representation, the fact that phonological representations, the fact that autonomous representation means that the element is always interpretable by the phonetics. So phonological representations are characterized by full phonetic interpretability at all levels of the derivation. I'm sorry, this is very small, but it's just the text from Harris and Lindsay, and it's that the phonological component is not a device for converting abstract lexical representations into ever more physical phonetic representations, as assumed in underspecification theory, let's say. Instead, it has a purely generative function in a technical sense that it defines the grammaticality of phonological structures. So the representations are uniformly cognitive. The primes they contain, unlike orthodox features, do not recapitulate the modality-specific details relating to vocal or auditory anatomy. And the processes are purely generative in a technical sense of specifying the membership of the set of grammatical phonological structures in a language. Under this view, the initial and final representations of a derivation are isotypic. They're processes that map phonological objects to other phonological objects rather than onto phonetic ones. So as such, we're firmly in the grammatical camp. So why does the identity of the features matter? Because if we take just terminologically the underlying form to mean the representation that you have before computation, so your features and your tiers, and surface forms, which are the representational output of the phonological computation, then that surface form is the thing that gets shipped into the phonetics module. Now, if you take Vollenhout and Ries's model, the surface form is made of features with a deterministic and universal articulatory-based instruction. So assuming that the phonology computes over articulatory-based features, like an SPE, this inhibits the analytical power of feature spreading in the analysis, because those features at the end, those features have to end up where they are, and they have to be the ones that are correspond to articulation. So this complicates the nature of the rules that we have. In element theory, the features spread freely between consonants and vowels, so the phonetic interpretation is variable. It depends, though, on association. So the feature might have a different interpretation if it's attached to a C in the skeleton, like in the syllable structure, into a V, into both C and V, or V and C in an autosegmental manner. The mappings are not universal or deterministic, so they are language specific. They're part of what you learn when you learn the phonology. Now the feature, the CV tier, the operations and so on, that's all UG. And the articulatory features, in the sense of the articulatory, all of the actual articulatory instructions and so on are all contained properly in a module, in a phonetics module, which is posterior to phonology. So all of the articulatory instructions, if you like, are mapped from the phonology, but they're all properly contained in the phonetics, and anyway. So the empirical patterns, there are lots of empirical patterns that are best analyzed by spreading. Obviously, most of phonology and vowel harmony previously, I mean, there are non-spreading analyses of these, of course, but these are often very intuitively seen as spreading analyses. But there are also lots of consonant and vowel processes, which would be all processes mixing segmental and prosodic conditions that seem like they would take well to a spreading analysis. So we've got Irish, short vowels, Bacchus allophony, Marshallese, consonant harmony, which is partly expressed by secondary articulations and also affrication in some cases. Extensive patterns of consonant and vowel distributional restrictions that are best analyzed in Serbian, Serbo-Croatian, which are best analyzed as being features that are shared between consonants and vowels. That's the Moran's theory that we just heard, the parallel structures model, that explicitly cites element theory as an antecedent because of this property, and consonant tone interactions. So tone on vowels having strong distribution restrictions with preceding consonants. You want the same features to be spreading in these cases to give you depressor effects, like in Liu's 2019 PhD dissertation. So look at the Irish, and Pavla's here, so I best be careful. But like the point is that in Irish, the short vowels are allophonic, in the sense that the backness of the short vowels depends on the palatalization or vedarization of surrounding consonants. Now, if you do this in an SPE type way without spreading, you're going to have these two different rules, underlyingly three vowel systems. You're going to have underlyingly three vowel system with those vowels, and then vowel separation rules such as vowel becomes back in the context of this, and so on. But Ciran, who does the analysis in element theory, has a spreading condition where he just has the feature of the consonant and the vowel spreading into each other to produce all the versions. Now, this is also possible autosegmentally using SPE features, because we're lucky that many people accept the plus and minus back feature applies to both consonants and vowels. And therefore, it was possible to have a non-low vowel analysis, to have an analysis where non-low vowels are underlyingly specified for plus back, and they're spreading the back feature between the vowel and the consonant. So the reason why that's possible is because we can share that feature, and it's widely seen as a better analysis than having a series of rules. Now, in my remaining time, I'm going to try to present, if I can, DREW, which is based on Data, I could have taken other examples like Inuktitut sorry, but it's nice to use this example, which is new. It's from Hale and Kissock from the MFN. Some people might remember this talk just recently. So in this language, we have this vowel inventory. You see E, E, schwa, U, O, and A. And we actually have
That's 9 minutes, by the way.
Thanks. So we have two types of E in German. We have fleeting E, and we have fleeting E, which you can see in these loan words here, like in jug and in saddle, where you don't pronounce the final E. And those, you pronounce faintly those positions. And we have raising in the context of after certain consonants, after palatal, so after S and Z in the orthography. The E there is sorry, the E there is a raising that we get of the same vowel. You see Greece becomes Gilisi. Now, the high vowels become fleeting in reduplication. So there's a reduplication process producing like light rain, eat rapidly, and so on. And you can see that the word final high vowels become fleeting. They're bracketed here on the right, meaning they're fleeting. Now, non-high vowels do not become fleeting. So as you see underneath there with remove, break up, cut up, those non-high vowels are all non-fleeting in the reduplication. Now, there is also thank you. There's also I'm finishing up. So there's also a fixed E that behaves like a non-high vowel. And at the same time, there is a fleeting E that behaves like a high vowel. So we see both types of E. So what's going on? There are also lexical fixed E's, like in hate and pesse. These behave like the fixed E in the sense that they can occur after palatals and they do not raise into E. So what's going on? The inventory has two ears. One of them actually in element theory would have A and E, and the other one, it has 0. It's empty. It's phonologically empty. So why doesn't it, so what does happen? Reduplication. Reduplication doesn't copy a vowel without A. So the real A will get reduplicated. The not real A, which is just an empty set, will not, because it's in a natural class with E and U and things that don't have A. And then we have spreading, which is because it's empty, the fleeting E just raises into an E through consonant vowel spreading. So the E spreads into that position, and so we get E, whereas a fixed E actually has A and E, and therefore it doesn't undergo any raising. I had some more things, but I'm afraid I've run out of time. So all I'll say is that let's do substance free elements and then feed it to the phonetic module, and let's use spreading analyses. Thank you.
All right, wonderful. Thank you very much. Again, raise your hands if you have questions or type them in the chat.
Okay.
Heather, do you have a question?
Hi, I'm going to come in as a person who doesn't actually work in substance-free phonology. And one of the reasons I'm here, I'm trying to pick out actual reasons why you want to believe substance-free phonology in everybody's talks. And there's a lot going on. So I guess my question here for you, Shanti, is, do you think that radical underspecification, empty segments, is a key argument for substance-free phonology or not?
Yes, I think it is. The question is how do those things get phonetically interpreted, and is there a feature insertion by the phonology, like a sort of default insertion, or is there just a mapping to a phonetic form? And those are two different questions there. But yeah, they speak very clearly, I think, to substance-free phonology, because we have two things on the surface that are identical, and underlyingly they are phonologically very different. In the Drehu example, there's no reason to assume that there's any features at all in the fleeting A, as far as I can see. Like maybe there will be evidence, but we could have used a different example perhaps, but there seems to be no evidence for a phonological feature in there.
All right, Thank you. Apologies for the slightly short Q&As here, but we should move on to the next talk. So thank you again to Shanti. Our next speaker is Pedro Tiago Martins at the University of Ljubljana, and his talk is entitled "Some Ramifications of Biology for Phonological Architecture."
Okay, let me just share my screen.
Sure.
Okay.
Go ahead.
Okay. Can you see my screen?
Yes.
Okay. So first of all, very quickly, thank you, to all the organizers for inviting me. Thank you to Sammy for their very smooth exchanges over email and attention to detail. And also, I'm very glad to be speaking after the one person I know in person from the speakers, Shanti. So I'm going to start. So my title, Some Biological Ramifications for Phonological Architecture. Actually, not sure if this title is grammatical, but we can forget about that for a second. This is not strictly about substance-free phonology, but I think substance-free phonology lends itself very well to discussions of the kind that I'm about to have. So why substance-free phonology and biology? So I think substance-free phonology is the one framework or approach to phonology that cares more about the nature of phonological architecture, not just a theory that works. So it wants something that's not just logical, but also plausible, right? And we can confront this, for example, with the constraint set in OT. How does the brain or the phonological component know about markedness? This is kind of a problem. Or even the number of constraints, which according to an article from 2010, might go up to 1,666 in OT. And Volenitz in his PhD thesis, I think, says, and I agree, that this is a bit biologically irresponsible, right? Because if these are part of a phonological architecture, where they all come from, how do they all coexist at the same time? And a related example of what it means to have some kind of biological concern about the nature of language would be, there's the idea that merge evolved from a single genetic mutation, for example, because the formal description of merge shows that you cannot further decompose it. Therefore, some very famous people say, if you cannot decompose it further formally, biologically, its evolution has to be also irreducible almost. And the only explanation is a sudden single genetic mutation. Well, I think this is not the right kind of way to use biology in your theories of language or of phonology. First, because the former, the formal description does not imply any kind of, the complexity of the formal description does not imply any specific kind of biological complexity, because you have to go through many levels. So if you think of David Marr, for example, the formal description of merge will be at the computational level. Then you have to go to the algorithmic level, and there you need a certain kind of automaton, you need certain kind of memory. So suddenly the complexity starts opening up. And then when you get to the implementation, how is this physically implemented in the brain? Then the complexity really explodes. And at that level, at the biological level, you cannot say it's a single genetic mutation because the complexity has exploded already. And also there's the fact that there's no evidence to support this. Quite the opposite, it seems that if you model some kind of magical single mutation, it has a hard time surviving. And you probably have more more mutations with smaller moderate fitness effects. But anyway, again, back to away from merge, away from syntax, and then back to phonology. So why biology and substance-free phonology? The question of whether phonological computation is substantial or substance-free is very much a biological one. I think there's no other reason to really care, right? Because it emphasizes this tension between the two factors, like phonology as computation and phonetics as substance. Where's the line between the two? How much crossing is allowed when you describe the phonological component? Does it matter if you duplicate phonetic information in phonological theory? Is it superfluous? Is it fine? And the concrete question that arises from this are, for example, are features innate or learned? I'm not going to answer this question, but I will try to problematize some biological arguments for innate features from a recent paper. Both authors are present, recent Volenitz. And I will problematize some of these arguments to try to generate some discussion. So they claim features are innate. I don't have a clear opinion on this, but there are certain biologically based arguments. One is that, well, I'll just name them here and then I'll explain what they are. So there's a speech-specific respiratory mechanisms, and speech kind of depends on feature externalization. So you'd need features in place for these respiratory mechanisms to have evolved. Another argument is that neurons in humans, humans have such an amazing number of neurons that you could grant them innate features. And also a similar argument for the genome, that the human genome is so vast that a couple of base pairs could encode for features, so you could grant them innate features. So I don't have an opinion on whether features are innate or not, but I will go over these arguments and problematize them a little bit. So the argument of the speech-specific respiratory system. So the argument goes that speech is the externalization of feature representations. And because the respiration system seems to be adapted to speech, for it to evolve, features would have to be in place and therefore be innate. I think there's some work that puts this into question. One is that it seems that the monkey vocal tract is speech ready. There's work by Fitch and other people showing that, you know, if you forget about the brain, if you put a human brain in a macaque, they would actually be able to produce speech. So they would have a speech capable respiratory system, which shows that you don't seem to need features then to have a speech ready apparatus. And the other argument would be that speech and respiration actually go hand in hand. There's a lot of work on oscillatory commonalities between respiration, chewing, and speech. They all seem to go hand in hand. So it's hard to say that one evolved and then gave way to the other. All of these things seem to have evolved at the same time and already present before humans existed. So I think this cannot be used to claim that features are innate. The other argument would be, so ants have seemingly innate navigational abilities and their brains have only 250,000 neurons because humans have 86 billion. I wrote here, it is likely, but it's more fairly, I should say, you could grant humans innate features if you have such a rich neuronal, such a high number. Well, in terms of number of neurons, the human brain is actually just a scaled up primate brain. It doesn't have more neurons than you would expect for a primate brain. There's a lot of work on this with a lot of comparisons between other species. And since we know that other species are speech ready, it seems that number of neurons wouldn't give you a good argument for claiming that features are innate. And also the number of cortical neurons cannot really be used as an argument for innateness of any one cognitive feature because humans will always win. Humans have more cortical neurons than any other species. So to use this as a justification for any of the innateness of any linguistic machinery or cognitive machinery will never fail. So it's a problematic argument. And then a similar one would be the genomic argument. So there are 3 billion base pairs in the human genome. So a few of them could code for the proteins that play a role in building the brain tissue responsible for the features. Therefore, this could be good indication that features are innate. I think this argument also needs some qualification. First, because the road from genotype to phenotype is complex and tortuous. This is also why the merge story doesn't really pan out. And it's not really known how many base pairs would be a reasonable number to encode for this, because there's no theory connecting the genome to linguistic structure, right, or to linguistic machinery. And as with the previous argument of the neurons, you could say this for any kind of linguistic machinery, and without a linking hypothesis between genotype and phenotype, any allusion to the connection between the two cannot be used to corroborate the innateness of any linguistic machinery. And this is something that David Popel and David Embick have written about indirectly. The granularity mismatch problem, for example, the units we work with in linguistics are very different from the ones people work with in biology, and you need a very strong linking hypothesis to be able to use each of the levels to justify claims on the other side. So the challenge would be around 9 minutes. Thank you. The challenge would be more work needed in biological grounding. For example, more in-depth comparative work. I think one of the things people tend to say, usually syntacticians, but they say, you know, only humans have language, so what are you going to look at? But comparative work is possible if you start decomposing capacities into more generic capacities. into other levels of analysis. And for example, Bridget Samuels, who is in attendance, she's written a paper comparing human phonology to birdsong, which I'm not really sure why this paper is not more well known and more cited, because it shows you the kind of comparison that's possible. You can compare already at the phenotypic level phonology and birdsong, then you'll find differences, but this is what allows you to start delving deeper into the biology, because then there are more claims that you can make. And if you combine these neurological hypotheses with genomic investigation, thank you, almost finishing. Here you can start to make more connections, going from the neurobiological hypothesis, and you can study things like gene expression in brain areas, and then you can start making some very indirect hypotheses, but it's very hard, I would say. And then I think it's also important to think of the role of emergence as a byproduct of cultural transmission, emergence of linguistic structure. I think that the problem is not just is this part of the innate machinery or not. Linguistic structure could emerge from cultural transmission. Simon Kirby's group works on this a lot. So I think the overall message of my talk would be, when grounding cognitive machinery in biology, namely linguistic machinery, we have to pay a lot of attention to biological over merely logical arguments, which will work but might not be plausible. And without the above, it could be that Foreman analysis is actually still the best way we have to form nativist arguments about features. I'll just finish with a quote from Volinitz and Rees, which I think represents a good challenge. So the only sense in which an I language could in principle be directly observed is in terms of connectivity, since our current understanding of the neurobiological substrate of all modules of cognition, including I language, is very limited. The insight about the nature of I language that can be gained on these grounds is also very limited. I think this is true, and this is a challenge that we have to overcome with the biological grounding. So thank you very much.
All right. Thank you, Pedro. We have a question from John Roski, first of all, in the chat, which came during the talk. The question is, what is special biologically about speech? Many communities use visual manual or tactile modalities to externalize phonology, and features can be advocated in any of them.
Yeah, actually, I'm not sure if there's anything special about speech. If you define it as feature externalization, that it starts sounding more special, because then you're making allusions to phonology. But as a capacity, I mean, as I alluded to, there's work on other animals that show they are speech capable. So I don't think there's anything intrinsically special about human speech in that sense. And also evolutionarily, it's also a big debate whether, you know, different people have different ideas about whether speech, whether language is originally spoken or sign, or a mix between the two, or a competition between the two. But yeah, I don't think there's anything necessarily special about speech biologically.
Okay, thank you. I think we have the next question from Beno.
Hi, thanks for the talk. It was great. So I'm slightly tempted to comment on your comments on our work, but I actually won't do that at all here. I have a completely separate question related to that paper by Tecumseh Fitch that shows that primate vocal tract is speech ready. So, I mean, I read that paper a long time ago, so I don't remember the specifics, and that's actually what I want to ask about. Namely, did they show that it's merely the case that the vocal tract, its shape and biomechanics is ready for speaking, or did they actually show that the respiratory system allows for an optimal exchange between oxygen and CO2, for example, so that they are actually able to speak for 10 seconds, 15 seconds, 30 seconds, or 5 hours as humans are? So is it only speech ready in the sense that the vocal apparatus is shaped in a particular way, or does the entire respiratory and laryngeal and articulatory system support speech?
Okay, so they had an older paper, which would be the shaped in the right way argument, from 2001, where they say that actually, because there's this, you know, this idea that we all learn in phonology or phonetics 101, that the human vocal tract is specially shaped for speech, and that's why other animals can definitely not do it. But they had a paper from 2001 that really showed that that might be not the case. And then in this paper, what they did was actually they analyzed living tissue, and they modeled the vocal tracts, and they were able to, well, make it speak, let's say. It's not very pleasant speech, but they claim that it will be able to hold contrasts, the contrasts that you could build a phonological system or externalize a phonological system with that vocal tract. And actually there's some sounds that they generated with some computer simulations. So I think they are really claiming, and I don't know if there's been work refuting this, that in an alternative universe that monkeys have the right brain for it, they could actually speak.
All right, thank you. We had questions from Shanti and Tobias, which we unfortunately will not have time for now. So Shanti and Tobias, if you want to reach out to Pedro separately with your questions. And yeah, let's thank Pedro again. We have to move on to our next talk now, which is by Max Papillon at Concordia, and it's entitled Linear Order and Simultaneity in the Phonological Representation. So Max, if you want to share your screen and unmute yourself.
Hi. Okay, this should be visible.
Yep.
And there we go. So my goal today is very humble. My big goals, I guess, is to introduce a glimpse of precedence relation-oriented phonology, or which I will call PROP from now on, which is for the approach that I developed in my dissertation from last year. And in it, I propose a representation with fewer stipulations that can capture simultaneity and order in phonology in interesting ways. So for this, I will talk a little bit about the background on strings and Ramey 2000 and his approach to reduplication. And I will talk about two things very briefly: vowel harmony without any association lines, without spreading rules, without feature copying. And I will talk about metathesis without string reversal. So strings and what they mean. So if you're a computer scientist, this will be very not enough, but for everyone else, like a string, if you're a phonologist, it looks like what you have at the top. You have a beginning of a word, and you have an end of the word, and you have a bunch of segments in between. And we could be a bit more explicit about it. Say, okay, there's a beginning of the word, it precedes the A, which the A precedes the B precedes the C, and so on. Because there's clearly no left to right order of orthography in the brain. So in the brain, we'd have to have some representation for this linear order. But also, once you've represented it in this way, in this very explicit way, you also have to say, okay, also none of those are allowed. There is no branchings, there is no loops, there is no self precedence. Well, what if we abandon those restrictions? What if we say a phonological representation is a set of precedence pairs among segments, a beginning of a word and an end of a word? So it would look like what you have in here with a set of ordered pairs of segments, or with a start and an end. It would come out as a graph. And what do we gain if we use this as a representation? What do we lose? My argument is that we gain all these new, for sure we get all these new possible configurations with loops, with branchings, with things preceding themselves, with parallel structures like this. And do we lose any restrictiveness? I think not. I think that in fact, if you do phonology in this way, it matches exactly what we need from morphology and phonology, from the way that things need to attach together. It just matches very well. So where does this come from? This comes from Ramey 2000, so who gave us a way to conceive of reduplication representationally. You have vocabulary items that come from the lexicon as graphs. The graphs affix to each other onto a stem, and the reduplication is just the special case where you form a loop in the representation. So if you look at the bottom left, you would have a root dog. You would have a suffix that seeks a last segment and carries a Z and seeks the end of the word, and it would form a graph like dogs. And in reduplication, you would have a root, you would have something that looks for a last segment and a first segment, attaches together, and it creates a loop. So, and if you just assume that these kind of loops need to be pronounced by going through the back loop and pronouncing everything twice, you get reduplication. It's a pretty simple assumption. You need to talk about the algorithm. There's a lot of literature on this. I have a recent paper upcoming in Sigmorphan proceedings and just put on Leanbuzz about this if you feel like reading about this, but this is not the topic of today. Because I want to talk about vowel harmony, because once you have this kind of representation, one thing you can do is put stuff in parallel. You can imagine it as playing the piano with two hands. You need a specification for one hand, one for the other hand. And here we just say, okay, yeah, you have stuff in parallel. You have an X, a Y, a Z, and you have a W that's pronounced throughout. So here, something that on the surface would look plus round plus high could underlyingly, or at some point in the phonology, would be a parallel plus round and plus high in the representation. So to do vowel harmony with this, we can take Finnish harmony where you have front words and back words that take respectively front suffixes and back suffixes. And when you attach them when you do that with parallel things, it would look something like this. All the front words would just carry a minus back in parallel, and the back words would carry a plus back in parallel. So what do we get from this? Well, we get vowel harmony for free. There's nothing else to say. When you put a suffix, it's automatically put in parallel. So here you have the la suffix that's put directly in parallel to the minus back, and here the la suffix directly in parallel to the plus back. It might be a bit geometrically confusing. Here's just stretch out the top. I just stretched out the top graph. So you can see that when I put the suffix, it was put directly in parallel to the minus back, and there's nothing else to say. If you just say that during these underspecified odds that I put in the representation, there's the minus back that's pronounced throughout, you get vowel harmony pretty much for free. Now, of course, vowel harmony is super complex. If you feel like reading about opacity, or if you want to look at interesting cases of phonology in Digo, read my dissertations. I do not have time to cover this today. But I will just switch to another thing that is cool is metathesis. So in Faroese, the well-known example of phonology condition metathesis is the masculines that end in sk, and while the neuters end in x. So Buckley, like everyone else, has to analyze this as a reversal because there is no other possibility in the string. You have the S before the K or the K before the S. There's no other way. With strings, yeah, that's really the only possibility. But once you allow for parallel structures, you can do interesting things like this. You can have the S and the K in parallel, and then it's a matter of which suffix you add that either adds an arrow from the S to the K or from the K to the S. And now this looks very simple, but you can do very interesting things with the more interesting case of Rotuman metathesis. So Rotuman, as a bit of background, has this complete and incomplete form, and the incomplete is always predictable from the complete by just reversing the consonant and the vowel, and then doing some phonology, the vowel sequence that you obtain in the middle. And sometimes the E becomes a Y. When there's two identical vowels, it tends to become a singleton vowel, despite Rotuman allowing long vowels. In some other cases, it coalesces. So this is all a complex scenario, and Besney's analysis is really a cool analysis in autosegmental phonology too. But here's how I can do it. You just say that the underlying forms of all these words has a V2 in parallel to the whole thing, and the complete adds an arrow from the consonant to the V2, which creates the unambiguous V1, C, V2 sequence, but the incomplete adds it the other way, with the V2 pointing to the C. And you automatically get the forms in B here when the two vowels are identical, because then you just get redundant vowels in parallel to each other. And for the rest, you can just apply the phonological rules to when they're in parallel. But like this also accounts for a lot of complications in the Rotuman that people don't usually discuss. For instance, there's these harmony patterns that emerge in only the incompletes that don't seem to be generic, like regular phonological rules of the language. They just emerge in this construction. And here I derive it by having this incomplete, setting up the vowel in parallel to the whole thing. You would get this E put in parallel to everything, and it would just be resolved with the same coalescence as is resolved in all of these other cases when you have an O and an E, or an O and A, U and E, and so on. So this is of course, gets also complicated. Here I have a little representation of clicks in Ta. I have allomorphy in Korean. I have, like, these are all other cool things that I can do with by putting stuff in parallel that we do not have time to cover today. And so I go see my dissertation if you just want.
That's 9 minutes.
That's 9 minutes and it's done. That's it. That's all I had to say today. Thank you.
All right, wonderful, thank you. We have a question already from Eric Ramey.
Yeah, hi, Max. Clearly, I think this is great. But one of the things that I always had trouble with, especially in convincing people to use the graphs, was kind of like the clumping into segments. And so I was wondering if you had any thoughts about kind of like how parallel phonology can go. Because like, so you've already expanded on, you know, how I was thinking about this. And so just like your analysis for Rotemon is great, because I puzzled on that thing for years and never came up with that. I think that's a really elegant thing or whatever. So let me sharpen this and then shut up. So we draw our graphs always with like basically segment sized things. And then you started showing that you can just do features in parallel to do vowel harmony. Even though it's graphically much more difficult, like how much should we be busting out the graphs into just parallel strings of just features and then have to have some sort of like kind of like clumping thing into segments?
Right, at this point, the new question that arises is, do we even need segments? Can we do everything by exploding? Like do we need V's? Or can we just say that there's a labial and a voice and all of this in parallel, right? That's right. I think that's the next obvious question. And aside of the graphical challenge, I see no reason not to jump on it. It's just going to take the page size graphs, but you're right. And I think I uncover many in my dissertation. I uncover a bunch of advantages of doing so, also for reduplication. So I think you're right. I think that's just the next step is, do we even need the segment, or can we just put everything in parallel and it would look like these very complex, complete, what are they called? Like
full graphs or something.
Full graph, or where you have a bunch of
Gantt charts.
Right. If you have a sequence TK, you have a minus voice and a minus voice. You have a coronal and a velar, and then everything connects to everything else. I think that's just the logical next step is, do we even need the segment? So I think you have a good point. Yeah.
All right. Then we have the next question from Tobias and then Heather.
I got two questions. One is, how do you do precedence when you align the specific vowel, which is on the upper arrow, with the consonant? How does the vowel know it gets to be linked to the consonant rather than to any other item?
Right. The idea would
be.
Sorry.
No, the other question is just in which way what you're doing is different from two auto-segmental tiers to communicate.
So the way it would work to be pronounced on the right segments I just need to say it's pronounced wherever it's phonetically compatible. So if T is somehow, at least in this language, or is specified as something that's not compatible with minus back, it won't surface as minus back. But I don't even need to say that all the time. There's usually a ton of what would be normally called co-articulatory effects on these consonants intermediate. But if you have, for instance, here this E in a back word would have to be opaque, and I would just say that it's specified as minus back, and therefore this plus back that's throughout is not compatible with it. So
you're saying it's predictable from what is compatible and what is not compatible?
I'm hoping that it would boil down to actual, like, phonetic, actual articulatory compatibility of the two things. You can't have your tongue front and back simultaneously, so therefore you have to pick one. And the way it would be picked would be by, like, I propose in my dissertation that when one feature is completely embedded within another, it's always the inner one that wins. And I think that there's reasonable non-linguistic reasons to believe this. Your second question was, I do not have the working memory for most.
Well, you already answered the second question. Okay. Which way yours is different from what you're doing is different from auto-segmental representation.
I think it's different. I think
auto-segmental
representation is recapitulating auto-segmental phonology. That's true. But I do it without association lines. I do it without special spreading rules. I think it's interesting just for the way to do it in the system that has nothing else. And it's just very
well, you had these little arrows between two floors of your representation, right?
Right.
And they go in different directions. Looks like association lines. But what you said is already is answering my question, because if you can predict what associates to what on the quote different auto-segmental tiers, you're not doing auto-segmental phonology, because in auto-segmental phonology anything can associate to anything in principle.
All right, thank you. I think we will have to move on there. So Heather, if you want to contact Max with your question separately. And let's thank Max again for this talk. We will now move on to a talk by Alex Chabot at the Université Côte d'Azur, which is entitled Finding Strength in Substance-Free Phonology. So Alex, if you want to share your screen and unmute yourself.
Sure, how do I share my screen?
There should be a button at the end, a green button that says share screen.
Yes, there it is. Okay.
Got it, perfect. Oh, sorry,
okay.
we can't see the full screen. Okay, now we can. Go ahead.
Let me just, can you see this? I'll just move it over here. Okay, so I want to present some data today from Campides and its Sardinian that I gathered during fieldwork last year to make a point about what substance-free phonologists have to learn and what people who are learning a language have to learn about phonology. So in substance-free phonology, typically we focus on melodic computation and melodic representations. Today, maybe it was the exception that proves the rule, where for the first time that I can really think of, we started talking about representations that are not strictly melodic. So one thing that we can do in substance-free phonology is make a phonological rule that does anything it wants with melody. So a P can be turned into an S in front of an R. And this is a sort of phonetically arbitrary process because it is not conditioned by any phonetic properties. But not everything in phonology is arbitrary, right? And I will go out on a limb and make some predictions. No language has more contrast in the coda than in the onset. There is no length harmony anywhere, and there is no open syllable shortening. One thing all those have in common is that they can be potentially traced back to properties in phonology that are above a representation of the skeleton. This is where phonology seems to be lawful. At the skeleton, since melodic computation could do anything, it is arbitrary. Above the skeleton, it is lawful. So what I think we need to do is any substance-free phonology needs a prosodic tier representation. And of course, this isn't surprising to anyone who worked in auto-segmental phonology or government phonology, but in substance-free phonology, it seems to me it has been given short shrift. Specifically today, I want to talk about strength and weakness in phonology, and I'm going to argue that I'm more going to talk about strength and weakness, but to talk about one, you sort of have to talk about the other. I think strength comes at this lawful prosodic tier representation in substance phonology. So one example, one manifestation of weakness might be the limited licensing power in weak prosodic positions such as the coda. And one representative of strength might be geminate inalterability, where what I'm going to argue is melodic material, which is multiply associated on the prosodic tier. And that's one way of deriving strength in substance-free phonology. It does not depend on the phonetic exponents. So if you talk about weakness, if you look in the literature, you might find all kinds of output-oriented arguments about what weakness is, which is given in terms of articulatory force or things like that. And that is not what's going to happen today. Because I'm going to argue the phonetic exponents of these structures, of weak structures and strength structures, can be phonetically arbitrary. So here's the first set of data from the Sardinian data that I'm presenting today. In A, you have a series of voiceless stops that are realized as voiced spirants when they are in intervocalic position. And in B, you have a series of voiced stops that fall in the intervocalic position. I should say about the data in B that this is a very variable phenomenon, and often people just don't drop the voice stop and it's just maintained. And when it is maintained, nothing seems to happen to it, okay? So the real interest today is what is happening in A, that is voiceless stops being realized as voice spirants. And I'm not going to talk about voiced stops in this context anymore today. I have another context that I do want to talk about where something interesting happens to voiced stops, where voice stops are realized as voiced spirants. A further context that complicates the surface pattern, because once again, we're talking about voiceless stops, but rather than being realized as voice spirants here in this intervocalic position, right? We're still talking about the intervocalic context. Instead of being realized as voiced spirants here, these voiceless stops are being realized with phonetic duration as long voiceless stops. Okay, so the point is here, since all of these contexts, all of these different alternation patterns are all happening in the intervocalic position, if we write a rule to do this for the voiceless stops, we are not being even descriptively adequate because of what is happening in 3. We need another tool to make sense of the pattern of alternation. So before I talk about the tool that we need, I want to zoom in a little bit closer on 3 specific contexts in Campanides Sardinian. The first one I'm going to call compensatory lengthening, and it is a post-lexical phenomena that happens after certain lexical coda consonants. So either the plural marker S or, for instance, the third person singular verbal marker T, which are not allowed to surface as codas, okay? So when the lexical coda is plugged into phonology, it cannot surface and it falls away. And any following voiceless consonant, as in A, is realized with length, and any following voiced stop, as in B, I'm sorry, I've made a typo. You should ignore this de here and focus on the underlying segment, is realized as a spirant, okay? The second context is a context of metathesis, where words that begin with a vowel and are disyllabic, R's that are in codas, that are lexical codas, can move out of that coda position. So as in A, when they move out of that coda position, a voiceless stop lengthens. And as in B, a voice stop is realized as a spirant, okay? And this is the same disjunction that we just saw in 4. The third context looks a lot like a case of radiopimento phonosyntactico, in which certain lexically specified words can trigger lengthening of a voiceless stop as in A, okay? But when that underlying stop is voiced as in B, once again, we get voiced spirants on the surface, okay? The same disjunction that we just saw. So essentially what we have here is a pattern that, looking at the bottom 3 contexts in this table, is that a pattern where voiceless stops are realized in length in this context, with length in this context, and voice stops are realized as short or normal length spirants. Okay, so my argument is that there is a direct link between the context of voiceless lengthening and de-spirantization, voiced spirantization. The conclusion being that despite the phonetic identity of de as a spirant, as voice stops as spirants, it is actually one of strengthening. It is actually one of phonological lengthening. And to suppose otherwise, in my opinion, is to interpret as an accident the fact that compensatory lengthening, metathesis, and radiopimento-induced compensatory lengthening all have complementary scope over voiceless and voice stops. So very quickly, why is this surprising? Because typically, phonologists are not comfortable with recognizing a spirant realization as a geminate or as some kind of fortition, okay? My principal argument here is that all three of these contexts are the result of a singular process of strengthening, which is reflected in prosodic structure. So basically all of those contexts are reduced to the following two contexts in Sardinian, where you have a process of lenition, which is not the one I'm going to be talking about today. Lenition works on melody, and you have one of fortition, which is a function of the prosodic structure. And it produces a surprising disjunctive output in Campbellian and Sardinian. So you can build, I have a theory of prosodic representation that I prefer. I'm not going to use it today because it's too complicated to explain in the time I have. So you can use just about any prosodic or autosegmental representation you want. And I'll be looking at all the contexts I just discussed real quickly. 9 minutes. Okay, I'll do this very quickly. I just have representations. In metathesis, we have a representation something like this. The R is going to be moved, right? Then it is going to free up this consonantal position for the k. The melody in k is then going to spread into that empty C position, and you're going to get a long surface consonant. The same thing happens with voiced segments. With voice stops, the R moves into this consonantal position, leaving an empty consonantal position, and the compensatory lengthening is actually something like compensatory spiritization in Sardinian. And then this would be the non-lengthening context, right? So these segments right here are actually realized on the surface as spirants.
That's 10 minutes.
But the underlying segment is a voiced one, not a voiceless one we've seen elsewhere. So this gives us our two different contexts. In A, we have the one for lenition or weakness. And B, we have the one for strength, where strength is a melodic, any melodic material that is multiply associated to two skeletal positions, given its strength, right? So the data show two things I think all substance-free phonologists need to take notice of. Strength and weakness are positional effects. They cannot be understood in phonetic terms. And we need to start talking about prosodic representation in substance-free phonology more often, okay? And I'm done. Thank you.
All right, thank you very much, Alex. Do we have any questions for Alex? Again, you can put them in the chat. You can raise your hand. If not, I had a quick question. I was wondering, so presumably in your analysis, we still sometimes say that spirantization of voice stops, for example, is lenition. So how do we go about, as analysts, as linguists, how do we find out when something is lenition fortition? I know you have in 12 here this structural difference, but as analysts, how do we go about finding whether we're dealing with 12A or 12B?
The particular theoretical tool that I use to do this stuff is CVC phonology. And CVC phonology doesn't have arborescent syllable structure. It is lateral syllable structure. One thing that you get out of it is a difference between onsets at the beginning of a word and between word medial onsets. Word medial onsets like this, and here in A, this would be an example of that. You have a specific lateral relationship that marks this C position here. And in that case, in languages where you have a lenition, any segment that would be in this position right here, whether it's voiceless or voiced, is subject to lenition. So it is a structural property of the lateral representations in that theory. But really, even with these simple representations here, I would expect that any time you have lenition of any segment in this position right here, it's going to happen to any leninable segment. The analysis has to build his or her analysis, their analysis, before they can identify where lenition or fortition are going to happen. But once they've done that, it should happen the same everywhere.
Right, thank you. Do we have maybe another short question for Alex? Yes, Pablo, go ahead.
Thanks. Yeah, I think just very, I know it's a big topic, very, very quickly. I mean, I think my impression, and correct me if I'm wrong, is that what you're basically saying is that what we see in the sort of supra-melodic domain is that there are laws, there are things that we cannot do with things that are not features, right? And then,
yes,
and then you're saying that, well, not features, elements, whatever you call them, right? And then below that, absolutely everything goes. Is there a particular reason you think that there are, I mean, or are there impossible operations on melody in the same way that there are clearly, impossible operations on?
No, I don't think, like in a rule that changes features or inserts features or deletes features, I don't think there are any phonetic restrictions. So, alpha can be turned into omega in the context of beta. That's not a problem at the melodic tier. At the prosodic tier, things just don't work that way. The reason, I think the advantage of this is that you reclaim a bunch of predictive power in your phonological theory about what possible and impossible languages look like. Because if I say on the melodic tier, anything can happen, I'm not making very many predictions about what languages are like.
Right, but that then, I think, what if your rule, what if all rules are auto-segmental? Right, then
what if all rules are
auto-segmental?
Well, I mean, if you can define, not all rules need to be structurally defined in terms of auto segments, right? Some of them, so if you have, I don't know, feature spreading that comes from us, that spreads back to a segment and immediately preceding segment, there's no real need there for auto segments that I can see. You can just describe it in terms of melody being spread from one segment directly back to another. And in that case, you don't need a prosodic representation. That's one of those melodically conditioned rules that can do anything, that can turn anything into anything.
All right, we should probably stop the discussion there. And thank you again to Alex for this talk.
Thank you.
Our next speaker is Marjorie Litzik at the University of Toronto. And she will be talking about Karaja ATR harmony and substance-free logical phonology. So Alex, could I ask you to hit stop share somewhere? And then Marjorie, you can share your screen and unmute yourself.
Okay, perfect. I just want to make sure that everyone hears me correctly.
Yeah, perfect.
Okay, great. So what I'm going to be presenting today, if my arrows can work, is essentially a partial analysis of Karaja harmony, specifically toward the mid-vowels. So Karaja harmony is a very complicated process, and I won't have the time to touch on everything that pertains to its ATR harmony pattern here today, but I hope that I can clarify certain things. And what I want to focus on for this talk is essentially regarding the conditions on the search and unify module that will be clarified, or the background will be given by Charles' talk a bit later today. But what I want to emphasize today is that we can have conditional unify, which can make reference to the termination of the search, and that these conditions can be different than the content of unify itself. So Karaja is a Brazilian language that features the ATR harmony pattern and whose surface vowel inventory is composed of 16 vowels. 12 of these vowels are oral vowels, and 4 of these vowels are nasal vowels. Underlying it, however, my proposal will be that there will be two mid-vowels that are unspecified for ATR. So there is a capital E, which is a mid-front unrounded vowel that has no specification for ATR. And there's capital O, which is a mid-round and back vowel, which is also unspecified for ATR. These vowels in Karaja can be grouped based on their behavior relating to the harmony process. So 6 vowels which are specified for place ATR are triggered to the harmony process. 4 vowels are opaque, so 3 nasal vowels and 1 low vowel, and 5 vowels are target vowels, including the 2 unspecified mid vowels that I will be focusing on. I will not be talking about the behavior of the high vowels because it's an extremely complicated behavior and it would take way more time than I have today. So Karaja harmony, as I mentioned earlier, is for the feature ATR. Specifically, we can describe its harmony pattern where the plus ATR feature will spread leftward. So it's a regressive pattern that is extremely strict onto preceding vowels that are target and will cause them to surface as plus ATR. This plus ATR, this regressive patterns, as I mentioned, is extremely strict. So the harmony pattern never progresses rightward. It never goes from the left to the right. With an example in 1 where we have our trigger vowel, which is a mid plus ATR vowel that will spread its plus ATR value onto the preceding vowel, so a high minus ATR vowel here, and or 2 unspecified vowels, causing them to surface as plus ATR. Number 2, however, is a case with opacity, where we have a trigger vowel that will spread its plus ATR value onto the vowel that directly precedes it, causing it to surface as plus ATR. However, the opaque nasal, the low nasal vowel that we have here, blocks the spread and also is not harmonizing, preventing this plus ATR feature to spread onto the leftmost mid vowel and will cause it to surface. Essentially, this opaqueness will cause this segment to surface as minus ATR. With regards to their possible combination for mid vowels, so where they can occur with regards to other vowels in words, there are 5 possible combinations. The first one is when our mid unspecified vowel surface, occurs when it precedes a plus ATR vowel, causing it to surface as plus ATR. All other cases, so whether a mid vowel is preceding a low vowel, a nasal vowel, a high minus ATR vowel, or even if it's at the edge of the word, will cause this mid vowel to surface as minus ATR. So in this case for Karaja, it seems that minus ATR is the elsewhere feature and that only the plus ATR feature is the conditioned one. So essentially a vowel will only surface as plus ATR if it's preceding a plus ATR vowel, otherwise it will surface as minus ATR. As a result of this, I have formed my condition for the search and unify model, where we have an initiator that will start the search process. And this initiator must be a superset of the minus nasal, minus high, minus low. So the initiator or the segment that will trigger the search for a feature to unify with will be a mid vowel. This initiator will be looking right, as indicated by the direction of the search. And the search will end when it finds when the initiator will find a terminator, which has an ATR value that it can unify with. However, there's an additional condition on the unification where the terminator must be a superset of the minus nasal plus ATR. In plain English, what these conditions essentially means is that a mid vowel will unify with the ATR value of the following vowel, only if this vowel is minus nasal and plus ATR. So if we have a mid vowel that looks right and find a vowel that is plus ATR but is also plus nasal, then the unification will not happen because the condition on unification has not been fulfilled. On the other hand, if it finds a minus nasal that is a minus ATR vowel, such as a high minus ATR vowel, then once again, or a low vowel, for example, then once again, unification will not happen because this vowel is not plus ATR, even though it is minus nasal. Additionally, we're going to need a second rule, a default feature filling rule, to account for the fact that minus ATR is our elsewhere condition. This rule will take any vowel and will unify it with minus ATR. In previous papers that went on to unification, it was already established that targeting all vowels to this process is not a problem because unification will yield 2 types of vacuous application, where a segment that is already specified for either plus ATR or minus ATR will essentially yield a vacuous application of this unification. So what this rule means essentially is that only under specified segments that are input to this rule will surface with minus ATR. My next 3 slides will be simple derivation, where I will show a case without harmony and then progressively build until we have cases of opacity. So in the 3 forms that we have, these are 3 roots that have various degree of disharmony in them. The first word is composed exclusively of mid vowels that are plus ATR. So these, because they are mid-vowels, are input to the MVH rule due to their status as a mid-vowel, so they can start the search. However, the result of this rule is going to be vacuous because they're already specified as plus ATR, so there can be no unification happening non-vacuously. And so the result of this is going to be vacuous. Then there are also going to be an input to the default feature filling rules because once again, these are vowels, so they are a target to this rule. But because they already have a specification for ATR, the result of this rule is also going to be vacuous, and they're going to surface as plus ATR vowels as they were in their underlying representation. For the second form, we have a plus ATR high vowel that is followed by unspecified vowel. This form is going to be an input to the MVH rule due to the status of this vowel here, the magenta capital E, which is a mid vowel. And however, even though this vowel is able to trigger the search, it will find itself at the edge of the word, and it will not find a vowel that it can unify with the feature ATR. And so the result of this rule is going to be vacuous because there is no unification that can happen. So this vowel will gain its minus ATR specification as a result of the default feature filling rule, which will fill it in with minus ATR, causing it to surface as a minus ATR vowel. Our third rule that we have here is a root composed exclusively of mid-unspecified vowels. Once again, this form is also a potential input to the MVH rule due to their nature as mid-vowels. However, the search does not terminate, it terminates at the edge of the word, and no unification can happen because neither of these vowels have a specification for ATR. So even though this capital O will look to its right and will find a vowel, it will not find an ATR value it can harmonize with, and so this vowel will be skipped. This will cause the result of this rule to be vacuous, and they will both gain their minus ATR specification as the result of the default feature filling rule, causing them to surface as minus ATR. Our next case is a simple case of regressive harmony. Well, I say simple, but it's also it's also quite interesting in that the first form especially shows an apparent iterativity where it seems that this plus ATR target manages to spread onto both of these vowels. What happens, however, is that both of these, this form is an input to the MVH rule due to their nature as being mid-vowels, and both of these will look at the same time to their right in search of a plus ATR vowels. Because they're looking simultaneously, there's no changes in the ATR specification for these unspecified vowels. So they will be looking right, and the first vowel that they will find will be this plus ATR vowels, and they will be able to unify with this plus ATR specification due to this vowel being minus nasal and plus ATR. So the result of this rule is going to be where both unspecified vowels will gain their plus ATR specification, and then they will, while they are input to the DFF rule, the result is going to be vacuous because they already are specified for plus ATR. The second form shows a case of strict regressive, where the vowel that has a plus ATR specification is in the middle of the word. So what happens is
9 minutes.
Yep, I'm almost done. So what happened is that this form is input to the MVH rule, and we have our mid vowel here that will look to the right, gain the plus ATR specification. However, even though these two vowels will be looking to the right and find this ATR specification onto the high minus ATR vowel, because this minus ATR vowel is not plus ATR, the condition on unification are not fulfilled, and they will not surface with an ATR specification through the MVH rule. They will instead gain their minus ATR specification as a result of their DFF rule. Lastly, what I want to touch on is the opacity. So in the first case, what we have is a case where we have our form that will be an input to the MVH rule, and this capital E will look right, find the low nasal, but the low nasal, because it's minus ATR, will not be able to cause unification. So the condition on unification will fail, and this vowel will gain its minus ATR specification as a result of the DFF rule. The second form that we have are three target
That's around
vowels.
10 minutes.
They will be looking right. They will find this nasal vowel, but even though this nasal vowel is plus ATR, they will not be able to gain this plus ATR specification due to it being a nasal vowel, and will instead surface as minus ATR vowels. So lastly, what I want to touch on is instead that this combination of conditions correctly managed to account for the fact that in Karaja, minus ATR is the elsewhere feature through the default feature filling rule, and also manages to account for the opaqueness of the nasal and of the ATR vowels. What is especially interesting here is that we can have a terminator and a conditional unifier that address the terminator, or essentially requires a terminator to be something, but they can be they can be featured differently. So they don't have to be the same. And the content of unify, so what the initiator will unify with, can be different than the conditions that will allow unify to apply. Thank you.
All right. Thank you so much, Marjorie. We've got a little bit of time for questions. So again, raise your hands or put questions in the chat. I see we have a question in the chat here. Ariwan, do you want to read this out actually?
I can read it out. It's fine, I don't mind. Or you can read it out
Right.
as well.
Yeah. So the question is, there was an example of lax u to tens u in one of the earliest examples. Was that a typo, or can vowel harmony be feature changing?
Yes, so vowel harmony can be feature changing, and that's why I did not want to touch on the high vowels, because the high vowels features a very complicated behavior where they're both targets, so they will both feature change. They will go from -ATR to +ATR, but they're also capable of blocking the spread from harmony onto the vowels that precede them. And because I didn't have the time, I was not able to account for them, but I'm currently writing a thesis on this, well, a master's project on this phenomenon, and it will be available then if people are interested.
All right, that was going to be my question as well, about what the high vowels were doing that was different. So thank you for addressing that. Do we have any other questions for Marjorie? Charles, yeah, go ahead.
I mean, if there's time, I mean, I guess part of the, if you had said more about the high vowels, I mean, you broke this into two parts: the mid vowel part, which you presented, and the high vowel part, which you didn't present. And so the example that Arwan points out is kind of evidence that they act differently, right? So it's kind of the justification for breaking it into. There's not just one rule of vowel harmony. Is that what you're getting at?
I think down the line we will be able to combine them into one rule because they are the application is going to be global. But I would really need to get into the behavior of the high vowels and the possible sequences and how they surface to be able to justify that. So for now, we could say simplistically that they can be broken down into two rules.
Thanks.
All right, let's thank Marjorie again. And with that, I think we are ready to move on to our final talk of this session. So this talk is presented by Vino Volanets at Concordia, and it's entitled Externalizing Substance-Free Phonological Primes. Where is yours, Vino?
Okay, thanks. Hi, everyone. Thanks for the invitation to speak here today. So okay, I hope you can see this. So I will be talking about how substance-free primes, specifically distinctive features that comprise your typical surface phonological representations, SRs, how these features are converted into speech production plans, by which I mean these fully specified instructions to the articulators. Or to put it differently, I will be talking about the transduction of SRs into speech production plans, which I tend to call true phonetic representations. So in order to be as clear and explicit as I can, hopefully avoiding some possible misunderstandings, let me lay out my starting assumptions. So the first assumption is that phonological primes are neural symbols. They are symbols in the brain. There's a rapidly growing body of work that suggests that phonological features correspond to some activity in the brain or some state of the brain. That's the first assumption. The second assumption is that phonological primes are substance-free. So again, to try to be as clear as I can, here's how I define substance. By phonetic substance, I mean the totality of the articulatory, acoustic, auditory properties of speech. So things like moving your tongue around, these measurable physical values like values of formants, frequency, intensity, or in psychoacoustic terms, loudness, then also duration expressed in milliseconds, and so on. So all this stuff is extra mental. So the second assumption is that features are devoid of phonetic substance. They are not articulatory, they are not acoustic, they are not auditory, they are neural symbols. So the second assumption follows directly from the first one. The third assumption is that speaking requires detailed neuromuscular plans. Basically, any neurobiologically grounded model of speech production that you look at, Levelt's, Hickok's, Genther's, contains a massive amount of detailed substance-related information about motor programs, their sequencing, temporal distribution, various layers of feedback, and so on. Genther's DIVA model is perhaps the best example of this. But of course, such detailed plans do not exist in surface representations. The whole point, especially historically, of substance-free phonology was that these things are phonologically irrelevant when it comes to phonological computation. But notice that there is a mismatch between the second assumption and the third one. So phonological primes are substance-free, but speaking requires detailed neuromuscular plans. So this leads to a problem, actually, that I will phrase as a research question. I will ask, how are features converted into articulator movements during speech, during the externalization of language? So one productive way, not the only way, but one productive way to figure out the answer to that question is to look at co-articulation, because co-articulation provides some important clues as to what is necessary for the externalization of these substance-free features. So it's useful to divide co-articulation into two types. The first type is called intrasegmental co-articulation. That's co-articulation between the realizations of features from the same segment, originating from the same segment. So for example, in U, realizations of plus round and plus high are co-articulated, and this leads to one specific type of lip rounding, roughly with more of a pursing movement of the lips, less rounding. In O, on the other hand, realizations of plus round and minus high, notice the difference, are being co-articulated, and this in turn leads to a different type of lip rounding with more rounding and less pursing. The other type is intersegmental co-articulation. That's co-articulation between the realizations of features from different segments. So the realization of plus round, if you have a token like this one here or this one here, the realization of plus round from U and O influences the preceding L. And interestingly enough, in these tokens, these utterances, both types of co-articulation appear on the lateral, on the realization, spoken realization of the lateral approximant. The crucial thing to notice that's depicted in these photos is that L is systematically different before U, as you can see, than before O. So you have an interaction between these two types of co-articulation. And so now we can, bearing that in mind, we can return to the original question: how are features converted into articulator movements during speech, during the externalization of language? So the theory of cognitive phonetics proposes that this is achieved by two transduction procedures. The first one is the paradigmatic transduction algorithm, or PTA for short, takes every feature from every segment and assigns a detailed motor program to that feature. Then we have the syntagmatic transduction algorithm, or the STA, which takes these motor programs and distributes them temporally. So the PTA assigns the motor programs, and the STA takes care of the sequencing and temporal coordination and distribution of these motor programs. That seems to be the bare minimum that's needed to externalize surface representations. And relating this back to the empirical data, you can see that PTA has the capability of accounting for intrasegmental co-articulation. To go back to the example, this algorithm will assign different lip rounding motor programs when it's externalizing the plus round of U as opposed to when it's externalizing the plus round of O, because of the interactions with different specifications for features in these two segments. At the same time, the STA can account for intersegmental co-articulation, perhaps more recognizable from the phonetic literature. Again, relating this to the previous example, the STA will then temporally extend these specific kinds of realizations of plus round from U onto the preceding L and from O to the preceding L. So it takes care of the transduction of features and has the power to account for various kinds of intersegmental various kinds of co-articulation and their systematic interactions. Interestingly enough, there's independent neurobiological evidence for this transduction system at the phonology phonetics interface. There are specific brain regions that execute the PTA and the STA, and importantly, they can be selectively impaired. So the PTA is carried out by the anterior insula, a subcortical structure buried beneath the boundary between the frontal and temporal lobes. The one that's important for speech is in the left hemisphere. And as demonstrated by this very influential paper by Nina Dronkers published in Nature, a lesion in the anterior insula leads to a specific apraxia of speech where all of the patients were unable to assign muscular activity to a phonological representation. And we know that these phonological representations were perfectly healthy or intact because speech perception, so transduction in the opposite direction, was working perfectly. On the other hand, the STA is carried out by the cerebellum, and cerebellar dysfunction leads to a kind of dysarthria, but a specific kind, which is characterized by temporal abnormalities in speech production. So you've got improper timing of articulatory events, coordination is relatively poor. There are delays or just general slowness in the execution of these movements, and so on. So to summarize and conclude, the conceptual minimum that's needed to externalize phonological primes are the paradigmatic and syntagmatic transduction algorithms proposed by cognitive phonetics. As I've shown on a simplified example, they can account for both intrasegmental and intersegmental co-articulation and for their intricate but systematic interaction. And there's an independent neurobiological evidence for them as well. Thanks.
All right, thank you very much. Do we have any questions for Benno? I see we have a raised hand here. Let's start with Sverre. Go ahead and repeat yourself.
Yep, thank you. So this second algorithm that I forgot the name of, the ETA, I think it was called, is there any reason why it has to refer to features and not, for instance, to motor movements or something like that?
That's a great question. In principle, I think it could actually refer to the whatever the first algorithm does. And it seems to me that the functioning of the STA, the syntagmatic, the algorithm that takes care of the sequencing of motor plans, coordination, and their temporal distributions, it seems that it is basically being fed by the first one. But this, I think this can be resolved, at least in principle, empirically, either by looking at how co-articulation works. And it seems to me that the example that I've given here shows that first you have intrasegmental co-articulation, which is taken care of, as I've argued, by the first transduction algorithm, and then the second one operates on that. So it does seem to be the case what you have said, basically, that it operates on the output of the first transduction procedure. Another way that this can be tested would be to look at how the brain executes these functions. Does the activity in the anterior insula precede the cerebellar activity or not?
All right, next we'll have a question from Bill Sardi.
Hi, yeah. So one of the major hypotheses in the birdsong literature, and then basically the hypothesis for vocal learning from Eric Jarvis, is that the animals that are capable of vocal learning all have direct cortical control of laryngeal structures. So really, how committed are you to the insula as the sole locus of your particular implementation of the motor planning? I mean, from what I can tell from looking at other animals, it's a very complicated matter, and I wouldn't think that that particular area of insula is the sole determinant of this?
Not extremely committed, not, well, if some specific evidence were to show otherwise, then definitely I would either abandon the hypothesis or modify it. The reason why I have taken the insula as the main locus of this transduction procedure is from lesion studies, Jonker's work, and then some other work as well. With respect to studies on vocal learning in other animals, I think a potential problem could be that, at least in my view, these animals do not have a feature system, or at least a human type feature system. So how the features are converted into motor programs that are then executed by the primary motor cortex seems to be a question that applies to humans. But of course, I'm not particularly completely committed to this hypothesis that it's only the interior part of the insula that's in charge for this transduction algorithm. So I would definitely be willing to modify or expand that hypothesis. And I can imagine that it would be reasonable to assume that the actual story is more complicated than that.
All right, and I think if we are quick, we can fit in both questions by Tobias Scheer first and then Joseph Ruwald.
Okay. Could you expand maybe on why the two different transduction mechanisms are conceptually necessary before talking about pathology? I know Bifon and other people do transduction with just a single mechanism. It depends, for example, on what you suppose the phonetic correlates or phonological items are. If you suppose like E or B values, for example, you don't need, as far as I can see, you don't need two different transduction algorithms. So what is the conceptual necessity of that?
Yeah, so I think the answer has two parts. One is like purely empirical, relating to this co-articulatory phenomenon, and the other one is neurobiological. So the first one is, it seems to me that if you're analyzing something like the differences, the systematic differences in the articulation of the lateral approximant in these two examples, the first thing that has to be transduced, I think, are the realizations of the features that are within the vowels themselves, because the L reflects the intrasegmental co-articulation that goes on with respect to the vowels. And specifically because in U, the plus round, its realization of the plus round feature will interact with plus high. You'll get one type of intrasegmental co-articulation, basically one type of lip rounding. In O, you'll get another type. And then these different types, only after the PTA has done its thing, can be transduced or operated on by the STA, so that you take this intrasegmental co-articulation and you temporally overextend it from the boundaries of the vowels onto the preceding lateral. And this is why the preceding lateral is pronounced systematically differently. That's one part of the answer. The second part of the answer, why? So the question was, why are they conceptually separated? It seems to me that they can be selectively impaired. So you can lose the ability to properly sequence and temporally coordinate, and just lose the ability to properly transduce temporal information separately from the disruption of the conversion of the SR into a motor program, leading one malfunction leading to a characteristic apraxia of speech, another leading to a specific type of dysarthria.
I see the pathology thing, but I was asking about the conceptual reasons. And what I've seen is that you have an analysis in your terms, but other people have other analyses that are also possible. So if you say that something is conceptually necessary, you say that there's no other possibility than doing it the way you do.
I'm not saying it's a conceptual necessity. I'm saying it seems to me that this story is the conceptual minimum that's needed, but I'm definitely not saying that it's absolutely necessary. And
Well,
the fact that other people have other ideas, I think, applies to every analysis of everything that has been said today. So it's not specifically about this, but
well,
I've said it, it's a conceptual minimum, not necessary.
But what does it mean conceptual though? Conceptual applies to everybody in the world, doesn't it? Right?
I'm sorry, I think we probably have to stop the discussion here. We're a little bit over time. We're running into our break here. Joseph Rual, Mike Stern, if you want to ask your questions to Vano in private, feel free to do so. So let's give a round of applause to Vano and to all of the speakers in this session. Thank you for an interesting set of talks. We will now have a 15-minute break. We'll reconvene here at 2:30 Eastern for the panel discussion. So if you want to, you can stick around in the Zoom room. If you want to, you can leave and you can go get yourself a drink, get yourself some food, as I will do, or whatever else you want to. So see you back here in 15 minutes.